1, 2,
Would it take some wind for the
4,
sound?
5,
If it could
6,
get the railroad for these workers, it could from
7,
it could be frank,
8,
it could be very frank,
2,
and clean.
1, 2,
Number
3, 4.
That extract from Philip Glass's Einstein on the Beach sets the scene for my maths and music talk today. In this talk, I'd like to share with you some aspects of music that have connections with mathematics. Because this topic is so enormous, I'll have to leave out many important areas and concentrate on just two that interest me. The first part of my talk will lead from the basic building blocks of rhythm, pitch, and harmony to a discussion of tuning and temperament. There'll then be a short break before the second part, which features the geometry of music. So let's start with rhythm, possibly the most fundamental feature of music, and one which is by its very nature mathematical. From ancient times, people have derived pleasure from the noises arising from beating flat surfaces with sticks or clapping one's hands. And a number of composers have incorporated such pitchless rhythms into their music. For example, the 20th century American composer Steve Reich developed this idea in his clapping games. Here's one of his simplest with two competing rhythms. Rhythm 1 is as follows. And here's rhythm 2. And when we put them together, we get a pleasant cross rhythm emerging, somewhat similar to the cross rhythms one finds in flamenco dancing. Another composition based on rhythm is a geographical fugue for spoken voices by the German Ernst Toch. It's based on various place names and begins like this: Trinidad and the big Mississippi and the town Honolulu and the Lake Titicaca. The Popocatépetl is not in Canada, rather in Mexico, Mexico, Mexico. And here you can hear, now you can hear the beginning of this piece.
Trinidad and the big Mississippi and the town Honolulu and the Lake Titicaca. The Popocatépetl is not in Canada, rather in Mexico, Mexico, Mexico. Trinidad, Canada, Mississippi and the town Honolulu and the Lake Titicaca. Trinidad,
And so it carries on. It then builds up and becomes quite complex. You can listen to it online if you're interested. Moving on to musical pitch, the connections with mathematics have been recognized for over 2,500 years. In Robert Flood's wonderful engraving, The Temple of Music, you can see many features, both mathematical and musical. And if you look at the archway at the bottom, you'll see a depiction of a well-known story enlarged on the right. According to legend, and surely untrue, the Greek mathematician Pythagoras was passing a blacksmith's forge when he heard the hammers giving off harmonious sounds as they beat out iron on the anvil. As he supposedly remarked, those hammers which gave the consonants of an octave were found to weigh in the ratio 2:1. I took that one which was double the other and found that its weight was 4/3 the weight of a hammer with which it gave the consonants of a fourth. Again, I found that the same hammer was 3/2 the weight of a hammer with which it gave the consonants of a fifth. It's said that to the Pythagoreans, everything is number, and that they aspired to assign simple whole numbers to everything, and in particular to musical intervals. Pythagoras was supposedly interested in music, as shown in this woodcut of 1492, though whether he played all these instruments is doubtful. More likely, he explored the notes produced on a monochord shown on the right, as he stopped the string in various places. In particular, as he may have discovered, and as the forged story recalls, a ratio of 2 to 1 corresponds to an octave, such as low C to upper C. Similarly, a ratio of 3 to 2 corresponds to a perfect fifth, such as C to G. And a ratio of 4 to 3 corresponds to a perfect fourth, such as C to F or G to upper C. The Greeks seem to have regarded such ratios as providing a key to the structure of the whole universe, as they were supposed to relate to the ratios of distances between the planets. How do we combine intervals? We simply multiply the ratios. So to combine a fifth, that's 3 to 2, and a fourth, that's 4 to 3, we multiply these ratios, giving 4 to 2, which is the same as 2 to 1, an octave. However, these Pythagorean intervals can give us problems if we carry them too far. Let's look at a modern piano keyboard and compare the ratio for 7 octaves with that for 12 fifths. Starting at bottom C on the left, 7 octaves takes us to top C on the right. And we find the overall ratio by doubling 7 times, giving 2 to the 7th, or 128. But for 12 fifths, we go through the intervals in red at the top, or around the so-called circle of fifths shown below, again ending at top C. For this ratio, we multiply 3 over 2 by itself 12 times, giving over 129. These two ratios are clearly different, even though they agree on the keyboard. Before we face this difficulty, let's look at the so-called harmonic series, also familiar to the Greeks, and see which notes we get when we take a vibrating string and divide it successively into 1, 2, 3, or more parts. Starting from bottom C, we get the octave above it, then G, then the next C, then E, and so on. These harmonics are also the notes we get from a valveless horn, such as a hunting horn or a garden hose, by increasing our breath pressure. They explain why two unlike instruments, say a violin and a recorder, playing the same note, can sound quite different. Each note is a different mixture of these harmonics. Several composers have used harmonics in their compositions. Here's the prologue from Benjamin Britten's Serenade for Tenor Horn and Strings, to be played on a horn without valves. And here I've added the numberings from the harmonic scale. As you'll hear, those harmonics with circles around them are at best approximations to the notes written, getting increasingly out of tune the further along the sequence we go, and producing quite an eerie sound. However, the numberings again cause us trouble. Let's try to spot some intervals from their position in the harmonic series. We'll start with 12 to 6, corresponding to the notes upper G and lower G. Here the ratio of 12 to 6 is the same as 2 to 1, and we indeed get the octave. Similarly, 15 to 10, corresponding to the notes upper B and the E below it. Here, the ratio of 15 to 12 equals 3 to 2, and we indeed get a fifth. And 12 to 9 is the same as 4 to 3, so we get a fourth, upper G to the D below it. But what about 13 to 9, corresponding to upper A and the D below it? That's also a fifth, but 13 to 9 isn't the same as 3 to 2. So again, we're in trouble. Later, we'll see how to get out of this difficulty, but it will be through a compromise. Basically, the Pythagorean system is flawed. But in spite of these problems, the Pythagorean approach to music came to play a prominent role in study and education. Plato, in his Republic, described the 4 subjects that he believed to be a necessary part of the education of the ideal ruler of state. The 4 mathematical arts of arithmetic, geometry, astronomy, and music, studied in the Pythagorean way. These 4 mathematical arts, later called the quadrivium, when combined with the 3 areas of the trivium, grammar, rhetoric, and logic, made up the 7 liberal arts, the cornerstone of learning from Greek times and into the medieval period in Europe until around the 17th century. If you'd been around at that time, you'd have studied these subjects too. Let's go back to intervals. As the years went on, there was increasing use of other ones, such as the major third with ratio 5 to 4. The major sixth with ratio 5 to 3. And the minor third with ratio 6 to 5. These numbers are a bit larger than the 1s, 2s, 3s, and 4s that we had earlier. But with these extra intervals, our earlier difficulties become even more horrendous than before. Here are 2 different ways of going up a tone from C to D. We can go via G and then via F. But the 2 ratios we get are different. Oh dear. A number of people try to smooth over the difficulties, such as the Mennonite friar Marin Mersenne, who's mainly known to mathematicians for studying the so-called Mersenne prime numbers, but who also wrote extensively about music, such as in the great monograph shown here. This monograph includes his enumeration of the 24 possible songs that can be made up from 4 notes. And he then went to write out in full all the 120 ways of arranging 5 notes, and even the 720 ways of arranging 6 notes, pages and pages of them. He also calculated a remarkable table giving the number of ways of making selections from a given collection of notes. Mathematicians know these numbers as binomial coefficients. His table goes up to choosing 12 notes from 36, which can be done in over 1 billion ways. This was the largest such number calculated up to that time, and it was all in a musical context. Meanwhile, the German astronomer Johannes Kepler had returned to the old Greek idea of musical intervals between the planets, the so-called harmony of the spheres. Here, the range of notes for each planet corresponds to the ratio of its speeds when it's closest to and furthest from the sun. So for Mars, where the ratio of the speeds is 3:2, the interval is a fifth. Whereas for Saturn, where the ratio is 5:4, the interval is a major third. And even Isaac Newton got in on the act. He wasn't musical. He once heard Handel play on the harpsichord, and all he could think of to comment on was the elasticity of Handel's fingers. But he spent much time trying to sort out musical scales, and he even tried to link the 7 notes of the scale with the colors of the spectrum, as you can see here. That's why we often say that there are 7 colors in the rainbow. It comes from Newton's linked researches into optics and color and music. To get around these problems, several different scales were proposed, and gradually the idea of equal temperament emerged. Here we give to each of the 12 semitones the same ratio, the 12th root of 12 to 1. That's about 1.059 to 1. This solves most of the problems, except that now every interval other than the octave is slightly out of tune. Here's a table comparing the ratios for equal temperament with the traditional ratios. The fifth is pretty accurate, 1.4983, compared with 1.5. As is the fourth, 1.335 compared with 4/3 or 1.333. But the major third, about 1.26 compared with 5/4 or 1.25 is rather sharp. So any piano tuned to equal temperament must be slightly out of tune. But the advantage of equal temperament is that we can now transpose from any key to any other. And here's a mathematical diagram that I once devised for deciding which of 2 key changes in a piece of music is the more remote. The 24 points correspond to all the major and minor keys, and the lines join keys that we consider to be related. Now on a piano, a key change from C major to G minor doesn't sound too bad. But a key change from C major to F sharp major really jars. And we can quantify this by looking at paths from one key to another. The longer the path, the more remote the key change. So C to G minor uses only 2 lines, whereas C to F sharp needs 6, so the latter is more remote. And you can use this diagram to compare any 2 key changes you wish and to see which change of key you need along the way. Coming back to equal tempered scales, there's no reason why we should stick to scales with 12 semitones, especially since we can now produce notes electronically as accurately as we wish. Why not have scales with 7 notes, for example, or with 31 or 53? In fact, such scales are already widely used in many countries and over many centuries. 7-note scales are used in Thailand, and scales based on 53 notes have been used in China. 19-note and 31-note scales are particularly useful as they give us very accurate fourths, fifths, and thirds. Here's a Baroque keyboard with 31 notes to the octave from Mersen's Harmonie Universelle. And such keyboards were actually built. In fact, Handel played on one. And several composers have composed in the 31-tone equal tempered scale. At the end of this talk, I'll play you one such piece. But for now, here's the beginning of a piece in the 19-note scale by the 16th century composer Nicola Vicentino. This concludes the first half of the talk. The second half will follow shortly.